So this is the last part of improper integrals. So in this section, what we're gonna do, improper integrals, we're gonna do test for convergence. Test for convergence. Test for convergence. So basically what we are doing is we're gonna answer a question like this. For example, if I say does the integral 1 to infinity e to the minus x squared dx converge or diverge? Okay, let's say converge. So if I ask this question, does the integral from 1 to infinity e to the minus x squared dx converge? The problem is if you try to use, because you know that this is a type 1 integral. So this is a type 1 integral. So if you type 1 integral, we know that when we have type 1 or type 2, we're going to use the definition and use the 3 steps. But when you write the definition and try to use the second step, in the second step what you want to do is you want to integrate the function. But the problem with this integral is you cannot integrate this. There's no way you can integrate this one. This is one of the integral that showed that you cannot integrate this using elementary functions. So that means you're going to get stuck with the second step. So that means you need a new approach. So what we can do in this section, we can talk about 2 interesting theorems. The first theorem is what we call the direct comparison test. So we call direct comparison. Direct comparison test. So in short we call DCT, the direct comparison test. Direct comparison test. And then we also talk about what we call limit comparison test. Limit comparison. Limit comparison test. So what we call LCT. LCD. So limit comparison test. Now if someone asks me, like, what is the best one out of the 2, it is mostly the second one, because the second one can be applied for many situations and also sometimes easy to handle because we consider a limit rather than the whole expression. But when you do direct comparison, the calculation can be a little lengthy because you can't directly compare with the 2 one. But still there are certain problems which are much easier to solve with the direct comparison test. But in general, the limit comparison tests are easier to handle. Okay, and then we also need certain tools. So tools are needed. So we can go with 2 things in this situation. One is when you do any of those results, so need another function to compare. So you need a function, new one. So need another function. Need another function to compare. So that part is there. You need another function to compare. And also we can use one of the results that we proved in the first part. We can use the p-integral test. So need p-integral test. P-integral test. So I hope you remember p-integral test. What is that? When you have the integral from 1 to infinity, 1 over x to the p dx, this is what we normally call the p-integral. This has 2 results. So one result is going to converge. It's going to converge if p greater than equal 1. It's going to diverge. It's going to diverge if p less than or equal to 1. So and if you want to remember this on a line, so what happened, the 1 is the one that divides the 2. So if you go to that side, this is where it's gonna diverge. So it's gonna diverge on this side and it's gonna converge on that side. So what's gonna happen here, it is diverge when it is less than or equal to 1. If it's greater than 1, it's gonna converge. So yeah, so we can remember this result also. And then also, there are certain things that you can remember. for example, this p need not to be this one not need to be 1. Actually, it can be any positive integer, any positive number. Okay, any positive number, not integer, any positive number. So yeah, so that is the what we call the p integral test. It is very, very useful in this chapter. We can use this a lot in this section. Actually, yeah, this will be very important in the next chapter when we talk about a series, convergence of series. We're gonna bring it to an integral and try to compare most of the time. And also there's a corresponding what we call p series. So this is the p integral, and then there's a corresponding p series as well. Okay, so let's try to develop the theories, and then but these are the kind of basics that you need to do a problem in this section. So let's talk about the basic theories. So what the first one is the let's write the theorem. So what the theorem is, direct comparison test. So direct comparison test. Direct comparison test, or in short DCT. So what the direct comparison test says that, so let's write it. Let f and g, let f and g be continuous functions. So let's say continuous on a to infinity, and let's say we have this condition. What's the condition? This is very important. And 0, so it's non-negative. So fx, and then gx is greater than or equal to less than. So fx is less than or equal to gx. So gx is bigger for all a greater than or equal a. So I'm sorry, for all x greater than or equal a. But even you can ignore some numbers from a, but even if this is true after certain number, so let's say a is here, but if it is like if your b is somewhere here, and if the condition valid after this, that's still okay. So but as a theorem we just write a, but you don't need really a, but it can be true after certain number which is greater than a. So that's the case. Okay, and then what it says, what the theorem says that there are two things. The first one is if the larger integral, that means a to infinity gx dx, that's the larger one, dx dx converge. So if the larger one converge, then the smaller one has to converge, because we know that this integral is area. So the larger area is finite, then the smaller area has to be finite. So it's kind of obvious result, okay, because these are areas. So then what it says that a to infinity fx dx also converge. So if the larger one converge, smaller one converge. Now let's look at the second result. But the second result says if the smaller one diverges, if the smaller one a to infinity fxd, that's smaller one, diverges, then the larger one has to diverge. Larger one means gx, gx dx has to diverge. So remember the order. So what we have is if the larger one converge, that's the larger one, converge, smaller one converge. If the smaller one diverge, larger one diverge, because these are areas. So it's very clear what we are talking about here. Yeah, so if you just draw some graphs, it can be clear. So for the first case, think about two functions like that. So this is the g function, this is the f function. So this is a g function, f function. What it says that the area of the larger function area of the larger function converge. So that means it's a finite area. So if the large one has a finite area, automatically, because a function is below the g function, the smaller one also should have a finite area. That's what the first one says. But the second one says, if the smaller one has an infinite area, diverge means has an infinite area, that means automatically the larger one should have an infinite area as well. So it should also diverge. So this graph kind of helps you to understand these two results. So it's one theorem but two results. Okay. So now let's try to see how we can apply this this kind of situation in a problem. So I'm going to do like several different examples. So even the problem that we could not do earlier, so we can do it right now. So let's try to study a few examples. So the first one, so examples. So let's say so test whether the following integrals converge or diverge. Test whether the following integrals converge or diverge. Converge or diverge. So that's the question. So test whether the following integrals converge or diverge. So let's look at the first one. So the first one is, let's say 1 to infinity sine squared x over x squared. So you can see that if you try to integrate this function, this can be very difficult, very difficult, because the format. So if you try to use integration by parts, or substitution, other substitution techniques, you can see that it's not easy. Okay, it's not easy. Sometimes it does even can be impossible. So what we're trying to do, we try to use this direct comparison result here. So what we're trying to do, we try to see whether we can find another function that you can compare with, which is either converging or diverging. But if you want to show that this one converge, then you want to find a larger function, the corresponding integral converge. If you want to show that this function is diverging, you want to find a smaller function, the corresponding integral diverge. So that's the kind of idea. So what you want to do, if you want to show that this converge, you want to find a larger function that can converge. If you want to show that this is diverging, you want to show that a smaller function that diverge. So that's what the theorem says. But what you do when you have this sine function, cosine function, what we normally do is we can consider this argument. So let's say notice that the sign is in between -1 and +1. Okay, that we know. So if you square this, you can see that when you square any number between those two, -1 and +1, what's going to happen? The square of this one is always in between 0 and 1. So that's true, right? So square is always in between 0 and 1. So because of that, what's going to happen? So then the integral converges. The integral converges. You can say since what? You can see that this function, the function in the integral sine squared x over x squared, is less than or equal 1 over x squared because of the observation. Why? Because we know that sine squared is in between 0 and 1. So if you replace sine squared by its largest value, if you replace this part by its largest, what's the largest value? Largest value is 1. So if you replace that by 1, it should be the largest. But then you can see that your integral becomes simple. It's just 1 over x squared. But when you have 1 over x squared, due to the p integral, this is a p integral with p equal 1. But we know that the p integral converge if p greater than 1. but here p equal 2. So that means this has to converge. So that means the corresponding larger integral converge. So the smaller one has to converge. Okay, so you can see, so let's continue, let's finish the argument. You can say on what, actually we need to say on what. So on, so this happen on, you can say 1 to infinity. Okay, that's where we interested. And so the integral converge since this inequality happens on 1 to infinity, and the corresponding integral 1 to infinity 1 over x squared dx converges since it is a p integral, that's what we call it, since it's a p integral with p equal 2, which is greater than 1. So that's the kind of argument, it's a mathematical argument. So we're going to kind of use this kind of wording for these kind of problems. You kind of identify that to a p integral, and then we kind of look for the properties of that. So what are the important words here? So notice that, so we have that, and then the integral converge, you need to write it, and then you also want to write the reason this integral converge since this property happens on this one, and the corresponding integral converges since it is a p integral with the p equal 2. So those things you have to write when you answer this kind of problems. Okay, so this is like a common thing. Okay, so I hope this is very, very clear, but you can see that how you get that function, you need to kind of think about it, what would be a best function. Sometimes what we can do, we can replace those sine cosine functions with this special interval. So let's look at another problem, and then it will be clear. So let's look at one more. B. How about this one? So let's look at 1 to infinity 1 over x squared minus 0.1 dx diverges. This one actually diverges because you see that if you subtract something from the denominator, that's get larger, right? That's get larger to the function which does not have that term. So that means you can see that diverge because this happens. What happens? 0 less than or equal 1 over x, because if you just remove 0.1 from the bottom, then you can simplify. If you remove 0.1 from the bottom term, then you can simplify, it's become 1 over x. So that means this is smaller compared to this one, because when you subtract something from the bottom, it gets larger. Okay, that's very clear. When you subtract, when you add something, it gets smaller. When you subtract something, it gets larger. So think about it, it's like a balance, it's a balance. So if you try to remove something, that side goes up. So you try to remove something from a balance, and you can see that that side is gonna go up. So I'm gonna draw a balance here just to tell you the idea. So so what you try to do, you try to remove something. So if you try to take something out, that side gonna go up. Okay, so think like that. So we try to take something out, that side gonna go up. So that's the kind of idea, that's the balance. So we can say on at the interval we have 1 to infinity, that's what we are interested in, and the corresponding integral 1 over x dx diverges. So you can see that the smaller one diverges. So if the smaller one diverge, the larger one should have a larger area. That means should diverge automatically by the direct comparison result. Diverges since it is a p integral. Since a p integral with p equal 1. Okay, so that's the complete argument. But you need to clearly say that it's diverge because the corresponding integral diverge, and it's a p integral, and that's the p-value. So those things are important when you make this kind of argument. Okay, so let's do another one. So you can see that you cannot use the same argument to show that 1 over x squared plus 0.1 gonna so I'll probably write this one here. So let's look at this one. So let's say 1, if we have the integral 1 to infinity x squared plus 0.1, if we have this one dx, now what's gonna happen, whether it's converge or diverge. And you can see that this one diverge, this diverge actually, this diverge, but we cannot use the direct comparison test to prove that. So this is a problem where we get stuck. Okay, so for this problem you cannot, because if you try to use the same thing, you can see 0.1, but you add this now. So if when you add, it's gonna, that side gonna go up. That's means the integral gets smaller compared to 1 over x, but 1 over x diverge. So the larger one, so the smaller one diverge here. So because this side is smaller, and then the other side is because if you try to do the same thing, this is what's gonna happen. So we know that because when you add something, so when you add something, this is smaller compared to 1 over x. But as before, we know that this one is diverging. So the larger one diverge. Can you say anything about the smaller one? No, you cannot say anything about the smaller one. Small one can be diverge or converge. So that means you get stuck. So that means you cannot use the you cannot use the direct comparison result in this case. You want to find something else. So that's why we need the new one, what we call the limit comparison test, so we can wait for that. Okay, so let's do something that you can do. So but here something that you get stuck, so you can't do this. So let's do another one. How about this one, because you also need to know what you cannot do, right? So the test also valid, the test also valid for type 2 integrals. Okay, this also valid for type 2 integrals. So let's do this one. So 0 to pi over 2 cosine x square root x converges. You can say converges because it's very similar argument. Because you can see because we know that on the interval from 0 to pi over 2, this is true. This integral is smaller than 1 over square root p on 0 to pi over 2. In that interval, cosine is in general you can write it, but because cosine can be negative, but on this interval that's true. So now what we're trying to do, we're gonna evaluate that integral. So let's go to the integral. So I'm gonna go to the integral and evaluate that. So it is as p integral. This is very easy p integral. So we can write the limit. There's a discontinuity at 0. So that means we can say a goes to 0 plus a pi over 2 dx over square root x. This is very easy integral. You can bring it to the top and then you can integrate. So you're gonna get limit a goes to 0 plus, what's the integral here? So integral is 2 square root x you can evaluate pi over 2 and a at those 2 points, and if you plug in those 2 points, so what you're gonna get, the limit a goes to 0 plus, if you plug in pi over 2, so it is 2 pi over 2 square root minus a square, no, 2 square root a, so we have 2 square root a, 2 square root a, and then a goes to 0 plus, that means this one goes to 0, so you simply end up getting what do you get? You're gonna get 2 pi square root. Okay, so that's finite. Okay, so the infinity is finite. So that means the larger one has a finite value. So if the large one is finite, so this larger one is finite. So by the direct comparison result theorem, this smaller one converge. Okay, so you can see so you can solve the integral pi over 2 dx over square root x converges. So by the direct comparison test, the smaller integral pi over 2 cosine x over square root x converges. Okay, so you can see that because you compare two functions, but you look at the larger one, but now you can see the larger one converge. So if the larger one converge, the smaller one has to converge. Good. So let's do one more. Remember the problem that you could we could not do, so we're gonna do this right now. So this is the e, so 1 to infinity e to the minus x squared dx converge. Actually you can see that this can converge, so converges because what's gonna happen, we know that because 0 e to the x is less than or equal e to the x squared on, not everywhere, on 1 to infinity. So if you have numbers which is larger than 1, you can see that x squared is bigger, and this is an increasing function. You can see that this exponential function is an increasing function. So exponential function is an increasing function. That means the larger values has larger images. Okay, so if we have x1, x2, so the image of x2 should be larger compared to image of x1. So the y2 is larger compared to y1. So that's the idea. Increasing function has a larger value for a large x. Okay, so this is true. Now what we can do, we're gonna make it upside down. When you make it upside down, what will happen is switch the inequality. So it's gonna switch the inequality when you make it upside down. You can divide. So then it's gonna go backward. Larger reciprocal of the larger one is smaller compared to reciprocal of the smaller one. So you can see converges because implies 0 less than or equal e to the x squared e to the x. So that means if the x squared getting smaller because that's upside down on 1 to infinity. Now what we're gonna do, we're gonna integrate the larger one, and when you look at the integral of the larger one now, so 1 to infinity e to the minus x dx, this is a very easy integral. So we can do limit. Now it is at the upper corner, so as b goes to infinity, we're going to integrate from 1 to b e to the minus x dx. This is a very simple integral. So this is limit b goes to infinity. We have negative e to the negative x and b and 1. So if you plug in the values, what's going to happen is the limit b goes to infinity if we plug in b, it is negative e negative b, and this becomes plus e to the 1, e to the negative 1. It's a negative 1. And then when you take the limit, what's going to happen when b goes to infinity? This term goes to 0 because of the negative power. So you simply end up getting e to the negative 1 or 1 over e. But this is finite because it's just a number. So the integral converge. So you can see, so the integral converge, okay, by the direct comparison result, because now you can see that the larger one converge. In this case, the large one is e to the minus x integral, so that but that's one converge, so the smaller one has to converge. Okay, so these are the kind of things that you can prove using the direct comparison result. Okay, so now let's try to move on to the other theorem. So what's the other theorem? This is more important. You can do many problems that you cannot do using the direct comparison, and sometimes it's even easier. So this is what we call the limit comparison. Limit comparison test. The limit comparison test as LCT, the limit comparison test. So if and g are positive, so we can assume that's positive. Okay, positive functions, and continuous, CDS, continuous on a to infinity, and we have this special result. The limit when x goes to infinity, fx over gx has a number, okay, finite number, has a finite number, okay, so has a finite number, so finite number, some number, it doesn't matter, but it has to be a finite number. Actually it can be positive because we assume that those functions are positive. So but we can kind of generalize this one for other cases as well, but we kind of at this time we kind of try to understand this one in this class. Okay, so it means so it's finite, so you get a finite number. So then what happen if this is the case? What happen if a to infinity fx dx, if one integral converge, the other one converge. If one integral diverge, the other one diverge, so they behave the same. Then and a to infinity gx dx are either both converge. The both is the important one. Both converges or both diverges. So what it says that they behave the same way. So that means if you know that the limit is a finite number, you take the limit. If it's a finite number, just the limit. So if one integral converge, the other one converge. If one integral diverge, the other one diverge. So here we are not going to compare with anything. We just take the limit and see whether it is a finite number. So if it is a finite number, what the theorem says, both behave exactly the same way. So let's look at an example, and it can be clear what we are talking about. So let's look at this problem. So let's do this one. So example, show that 1 to infinity dx over 1 plus x squared converges. Okay, so what we're trying to do, we try to kind of do a mental calculation and try to find a function that you can compare with. What we normally do is we kind of take those unnecessary terms out. For example, we have plus 1 here, we're going to take it out. We only consider the largest terms, just the largest terms. Okay, so what we're going to do, So the answer here is the function fx equal 1 over x squared as one function, and we're going to take the gx. What's the gx? We just remove those unnecessary terms, so that means in this case we're going to remove 1, so that you're going to get 1 over x squared. That's how you get. You only take the largest terms, okay, are positive, that's one condition, are positive and continuous, because it's continuous on 1 to infinity. That's where what's the limit integral is on, so 1 to infinity. So that we know that condition. And then what we can do now, we're going to consider what's going to happen in the limit. But note that the limit x goes to infinity fx over gx. So let's plug in. It's the limit x goes to infinity. This is one function 1 plus 1 over x squared divided by 1 over x. It doesn't matter which one. So we normally put the complicated one on top, okay, and then this one you can simplify very well. What we can do is the bottom one gonna get, when you divide, you can flip over, so that means it's gonna go x squared over 1 plus x squared. So that's what happened when you flip it over. And you can see that how to do this kind of problems. What we normally do is we can divide the top and bottom by largest term, so that means 1 you divide by x squared, so you can get 1 over x squared plus 1, and you can see that this term goes to 0. So this one goes to 0 when x goes to infinity, so you simply get 1 in this case. So you get 1, but which is finite, okay, so this is finite. So that means it's a number which is finite. You can see therefore the integral 1 to infinity 1 over 1 plus x squared converges since the integral 1 to infinity 1 over x squared converges. Why this one can converge? It is a p integral with p equal 2, which is greater than 1. Converges since it is a p integral with p equal 2, which is greater than 1. So that is the complete argument for this problem, but you can see that it's not that difficult. But this problem actually you can even use the direct comparison result to prove. So I'm going to put this as a note. We can also use the direct comparison result in this problem. Why? You can see that since 1 over 1 plus x squared is smaller than 1 over x squared. So that's the reason why we can do it. And you can see that now the larger corresponding large integral, which is a p integral with p equal 2, is going to converge. So this one converge. So in this case actually the direct comparison result is much faster, but there are some problems it's very difficult to use the direct comparison result compared to the limit comparison result. So let's look at one such example. This is the last one we're going to do for this section. So the last example, we're going to see test for convergence. Test for convergence. The integral 1 to infinity 1 minus e to the minus x over x dx. So this is a kind of integral that we're trying to test. But you can see that if you try to use the direct comparison, it can be very confusing here because we don't know even what to compare with. But if you go with the limit comparison, it's very easy now. So the answer, so let's see what's going to happen now. Okay, so let fx equal the one we have, so 1 minus e to the minus x over x, and gx equal 1 over x, okay, and they are positive, they are positive and continuous on 1 to infinity. So now what we can do, we can look at the limit. So the limit when x goes to infinity, fx over gx, and you write this just to make it complete, and the limit x goes to infinity, 1 minus e to the minus x over x, and then 1 over x, and you can see that 1 over x get cancelled because they are all both in the bottom, so they get cancelled. You can simplify the bottom and top separately, so that's a kind of valid argument. You can simplify the bottoms and simplify the top separately. Yeah, so you can see that this is the limit. X goes to infinity, once x get cancelled, you simply get 1 minus ex. Now you can see that when x goes to infinity, this goes to 0, so you simply end up getting 1, which is finite. Okay, this is finite, so that means it's a finite number. That means both integrals behave the same, but we know that the 1 over x is diverging because it's a p equal 1 integral. Yeah, so that integral gonna diverge. So you can see therefore, so it's a 1, it's a number, so that means the two integrals behave the same. So therefore, the integral 1 to infinity 1 minus e to the minus x over x dx diverges since the integral 1 to infinity dx over x diverges. Why? As a p integral with p equal 1, which is less than or equal to 1. So you can see that the amazing power of the limit comparison test. So there are a lot of problems that you cannot do using the regular method, but if you use the limit comparison test, you can do those problems. So make sure that you kind of go through this again and try to kind of distinguish how they behave differently. So this is the end of the improper integrals section. So we divide this into 3 parts: type 1, type 2, and this is the tests. Thank you.